Imagine this for a second. You're talking to someone maybe in a totally different language, right? But you hear their voice, like their actual voice, tone, and all instantly translated into your language. That's kind of the holy grail of real-time, high-fidelity speech translation. It's a massive challenge. And today, we're diving deep into a paper that tackles this head-on. It's called High-Fidelity Simultaneous Speech-to-Speech Translation. And it introduces a model called Hibiki, which I believe means echo in Japanese. A pretty fitting name, actually.
Yeah, exactly. Echoing the voice across languages, it's quite apt.
Okay, so for everyone short on time, let's do a quick, 1-minute rundown of the key takeaways. First up, Hibiki. It's a new model, decoder-only, handling both simultaneous speech-to-speech, S2ST, and speech-to-text, S2TT.
That's right. And the key is simultaneous. Unlike older methods that got to wait for the whole sentence, Hibiki works chunk by chunk in real time. Think more like a human interpreter than just a machine.
And the results. They're claiming state-of-the-art stuff, like really good translation quality, keeping the speaker's voice sounding like them, that speaker fidelity, and just making it sound natural, human.
A really big piece of the puzzle is this method they call contextual alignment. It's weakly supervised, and it basically lets the model figure out the best timing, the best delay for translating each word. Super clever.
And maybe the most practical part. The way it runs inference, the actual translation process, is simple. This means it can run efficiently in batches on GPUs, handling lots of streams, or even, get this, run in real time on a smartphone. That's huge for actually using it. Okay, so that's the snapshot. But, how does Hibiki actually pull this off? It sounds incredibly difficult. Maybe let's start by setting the stage. What's the fundamental problem with simultaneous translation compared to, say, offline translation?
Right, so, offline or consecutive translation, that's like dubbing a movie. The system gets the entire recording first.
It sees the whole picture.
Exactly. It has all the context, start to finish, but simultaneous. That's like translating a live speech as it happens.
Yeah.
You have to make decisions constantly with only the context you've heard so far. And that's incredibly hard for machines.
What?
When do you start translating? How much do you wait? Get it wrong and it sounds awkward, or you miss information. Plus, a massive bottleneck has always been the data. You just don't have much, if any, speech data that's perfectly aligned chunk by chunk between languages. So historically, people used cascaded systems.
Yeah.
Chain and ASR for speech to text, the machine translation for the text, then text to speech to make it talk again.
ASRMT/TTS, yeah, the classic pipeline.
Right, but it has problems. Errors pile up at each step. And crucially, that middle step, the text, it throws away all the non-word stuff.
Like the voice, the emotion.
Exactly. Speaker identity, prosody, intonation, gone. That's the text bottleneck.
Yeah.
You end up with accurate words, maybe,
Yeah.
but spoken in a generic, often robotic voice.
Right, which kind of ruins the whole point of hearing the person.
Precisely. And that's why end-to-end S2ST is the goal. Go straight from source speech to target speech. Keep all those paralinguistic details, especially the voice.
Okay, so Hibiki aims for that end-to-end goal. Let's get into its design. You said it's different. This is where it gets really interesting, right?
It really is quite innovative. Hibiki is a decoder-only model. So unlike models that have separate encoder and decoder parts, it primarily focuses on generating the output. And it uses a multi-stream language model. Think of it as listening to the source speech stream while simultaneously generating the target speech stream.
So it's listening and talking at almost the same time.
In a sense, yeah. It jointly produces both text and audio tokens. This lets it handle both S2TT and S2ST from the same underlying process. Under the hood, it uses nested transformers, global ones looking at the bigger picture, local ones focusing on the fine details. This helps model the two audio streams together. And for the audio itself, it uses a causal audio codec, specifically something called the Mimi codec. Causal just means it processes sound strictly in order, piece by piece, which is essential for real-time streaming.
Okay.
This codec turns the audio waves into discrete tokens, sort of like digital codes. Some capture the meaning, the semantics, others capture the sound, the acoustics, the voice quality.
So it digitizes not just the words, but the sound of the words too.
That's the idea. And here's a really neat twist. Hibiki uses the text. It predicts internally, they call it its inner monologue, as a kind of scaffold or blueprint to help generate the target speech when it's actually translating.
An inner monologue, like it's thinking in text before speaking?
Kind of.
Yeah.
And this is different from other models that might predict text but then ignore it for the speech part.
Yeah.
Here, it's integral. It even helps provide word-level timings in the target language.
Wow.
And maybe the biggest win for practicality is how simple the inference is. Just standard sampling methods like greedy decoding. No complex control policies.
Which means
it's super efficient. You can run tons of translations in parallel on a GPU badge translation, think hundreds of streams at once. And it's efficient enough to run in real time, right on a device like a phone. That's a game changer compared to models needing complex logic that slows things down or prevents batching.
Okay, that inference simplicity, that sounds huge for actually deploying this stuff. But going back to the simultaneous challenge, the timing, deciding when to speak, how does Hibiki learn that? What's this contextual alignment thing?
Yes, contextual alignment. This is probably the core innovation for handling the timing. It's a weakly supervised method. Basically, they don't need perfectly aligned speech chunks, which are hard to get. Instead, they cleverly use an existing powerful text translation model, MATLAB3B in this case. They use it to figure out, for each translated word, roughly when enough information appeared in the source audio to justify translating that word.
So it's using a text model to guide the speech timing.
Exactly. It looks at things like how much the likelihood of a target word increases when the corresponding source words arrive. This lets them generate synthetic training data with pretty good word-level alignments without needing painstakingly hand-aligned audio. They generate this data by taking single-language audio, getting transcripts, translating the transcripts using MATLAB, and then resynthesizing the translated text back into speech. Now, to get the audio aligned based on these text alignments, they have two ways. One is simple. Just insert silence into the target audio if it's getting ahead of the source context.
Just pause.
Yeah, simple, but can sound a bit abrupt or make the delay feel arbitrary.
Okay, makes sense. And the other way?
The more sophisticated way is alignment-aware TTS. This text-to-speech system generates the audio while following the timing constraints derived from that contextual alignment process. It's really smart. It can subtly insert tiny pauses like padding if a word needs to be delayed, or it can even slightly speed up the speech rate to catch up if it's falling behind the target alignment. It makes the timing much more natural.
So it's not just a fixed delay. It's learning an adaptive flowing delay, much like a human interpreter might adjust their pace.
That's a great way to put it. It learns when to translate dynamically. That's key to making it sound fluid.
Okay, that covers the timing and the words. But what about keeping the voice? You mentioned speaker fidelity. How does Hibiki actually make the translation sound like the original speaker? That seems like magic.
Not quite magic, but definitely tricky. A big problem is the training data. Standard datasets like CVSST, often used for this, actually have pretty low similarity between the source speaker and the target reference speaker, like an average score of only 0.23.
So the training data itself isn't great for learning voice transfer.
Right. So what the Hibiki team did was regenerate parts of CVSST using their own alignment-aware TTS system. This let them create target speech that was much more similar to the source speaker, boosting that average similarity score way up to 0.47. Better data to learn from.
Okay, better data helps. What else?
They also use conditional training. This is clever. Instead of just throwing away data where the voice similarity is bad, they label each training example with a score like very bad, bad, okay, good, very good similarity. These labels get turned into learnable embeddings, sort of like tags, that are fed into the model. So the model learns about voice transfer quality during training. Then, when they actually run the translation, they always give it the very good label as input, nudging it towards the best possible voice transfer.
Guiding it towards the good examples it saw. And I think you mentioned classifier-free guidance. How does that fit in? Sounds familiar from image generation models.
Exactly. It's a similar principle adapted here. At inference time, they actually calculate the model's predictions twice. One's conditioned on the very good voice label, and one's conditioned on the very bad label.
Okay. Why both?
Because then they can mathematically combine these predictions, essentially amplifying the direction towards very good and away from very bad. It significantly boosts the perceived voice similarity without hurting the translation accuracy.
But doesn't running it twice slow things down, especially for real time?
That's the beauty of it. They can compute both conditions, good and bad, together in a tiny batch size too. So it adds very little overhead and is totally compatible with real-time inference, even on the phone model. It's a neat trick to enhance quality without a big performance hit.
Okay, we've gone through the nuts and bolts, the architecture, the alignment, the voice transfer, but the real question is, how well does it actually work? Let's talk performance, the results. How does Hibiki stack up?
Right, the proof is in the pudding. And the results are pretty impressive. For translation quality, they use metrics like ASR BLEU. Higher is better. Hibiki hits 30.5 ASR BLEU, What's striking is that this score actually beats some offline models like Stream Speech, which got 28.5, even though Hibiki is doing it simultaneously, which is much harder.
Wow, better than models that get to see everything first?
In some key comparisons, yes. And when you compare it directly to other simultaneous systems like Seamless and Stream Speech, Hibiki generally comes out on top, especially on standard tests like CVSSC, French to English. Hibiki gets 39.2 ASR-BLEU there, while Seamless gets 37.0. It might have slightly higher latency sometimes, but the quality gain seems significant. And particularly on longer audio, Stream Speech apparently struggled quite a bit, whereas Hibiki handled it well.
Okay, so the translations are accurate, but how do they sound? What about the naturalness, the audio quality? Did humans listen to it?
They did. And the human evaluation results, using mean opinion scores, MOS, are perhaps even more compelling. On a 1 to 5 scale for quality and naturalness, Hibiki scored around 3.7, 3.8.
And how does that compare?
It's a huge jump from Seamless, which scored around 2.2 in the same tests. Hibiki scores are getting much closer to the scores for actual human-interpreted speech. So listeners found it significantly more natural, smoother, just better quality audio overall.
That suggests the alignment and voice transfer stuff is really working.
It seems so. The ablation studies, where they test the model with parts turned off, confirm this. Contextual alignment gave the best quality latency trade-off. Trying to translate with no delay was terrible. Fixed delays were okay, but slow. And removing that inner monologue text prediction also hurt performance, confirming it really does act as a useful scaffold for the speech generation.
Makes sense. So we know it performs well in tests. What about actually using it? You mentioned the simple inference helps.
Yeah, that's where it shines for practical use. The batched inference capability is huge. They showed it processing over 300 streams simultaneously, faster than real time, on a single high-end GPU. That's ideal for scaling up a service.
300 streams.
Yeah, wow. And then there's the Hibiki M model. That's a distilled, smaller version, about 1.7 billion parameters. And they got that running in real time on an iPhone 16 Pro, even with the classifier-free guidance for better voice quality.
Real-time, high-fidelity translation on a phone. That's pretty amazing.
It really bridges the gap between research and real-world application potential.
Are there any catches, limitations mentioned in the paper? Areas for future work?
Sure, they're upfront about that. This work focused mainly on French to English. Scaling to many more language pairs would require building out robust TTS systems for all those target languages. Also, while it's great at matching the style of its training text model, MATLAB, they suggested using even more diverse or perhaps human-generated translation targets during training could potentially push the absolute translation quality even higher. But these seem like engineering challenges rather than fundamental flaws.
Okay. So wrapping this up, Hibiki feels like a really significant step, a big leap forward in making simultaneous speech translation not just faster, but also much higher fidelity, much more natural sounding. That Echo name feels earned.
Absolutely. And for everyone listening who's in the tech space, this paper is important. It really pushes the envelope on real-time AI communication. It shows how smart architectural choices, like the decoder-only design, and clever data handling, like contextual alignment, can overcome really tough challenges. It makes something that felt futuristic seem much more achievable, and efficiently so.
Yeah, it really makes you think, how could a technology like this, once it's mature and widespread, change things? Global business, travel, education, accessibility, even just chatting with people anywhere. The potential impact is kind of staggering. If you're intrigued by this, the paper mentions publicly available samples and code. We definitely recommend checking those out to actually hear Hibiki in action. It's one thing to talk about it, quite another to experience it.